this episode, we're going to talk about model theft, which is the problem of someone trying to copy the value of your model without actually obtaining it through legitimate means. For beginners, it can help to think of a model as a product, not just a piece of software. A trained model represents time, expertise, compute cost, and often unique data. If an attacker can recreate a close approximation of it by interacting with it, they can steal that value, compete unfairly, or use the copied model for harmful purposes. Model theft is sometimes called extraction because the attacker is trying to extract the model's behavior through queries and outputs. This can happen even when the attacker never sees the model file itself, because the model's responses are a kind of interface that reveals how it behaves. The risk is not only about business loss. It can also create security issues when a stolen model is used to discover weaknesses, bypass safeguards, or accelerate other attacks. Preventing model theft requires understanding how extraction works at a high level, why query access is such a powerful lever, and what practical defenses, including query limits and watermark strategies, can reduce the risk. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to clarify what it means to steal a model in practice. Attackers do not always need a perfect copy. They may be satisfied with a model that behaves similarly on important tasks. In many cases, they are trying to build a substitute that is good enough to replace the original for a set of users or a set of functions. They might also be trying to replicate a specialized capability, such as how your model answers questions in a particular domain or how it follows certain internal style rules. In classification systems, attackers can sometimes build a replica by collecting many input-output pairs and training their own model to mimic the target. In generative systems, attackers may do something similar by sampling the target model's responses across many prompts and using that as training data. Beginners should notice that this looks like a learning problem. The attacker is turning your model into their dataset. The more access they have, the easier it becomes. So the model's interface is both a feature and a risk, because every response teaches an observer something about the model's behavior. Extraction risks are shaped by what the attacker can observe and control. If the attacker can send unlimited queries, they can cover many parts of the model's behavior, including edge cases. If they can craft inputs strategically, they can map decision boundaries and discover how the model reacts to subtle changes. If they can see rich outputs, such as detailed probability scores, they can learn more efficiently than if they only see final answers. Even in generative settings, output richness matters, because longer and more detailed responses provide more training signal for the attacker. Another factor is consistency. If the model behaves deterministically, producing the same output for the same input, an attacker can collect clean training pairs. If the model has some randomness, extraction becomes harder because the mapping is noisier. Beginners should see that the attacker's goal is to reduce uncertainty about the model's behavior, and their tools are volume, variation, and measurement. Every design choice that reduces the attacker's ability to measure and repeat helps reduce extraction risk. There are also different flavors of model theft, and understanding them helps you choose defenses. One flavor is black box extraction, where the attacker only interacts with an interface and never sees internal details. This is common for hosted AI services. Another flavor is white box theft, where the attacker steals the model file directly by compromising storage or deployment systems. Black box extraction relies on queries, while white box theft relies on system compromise. Both matter, but the episode title focuses on extraction, which is the black box pathway. Another distinction is between copying the model's core capability and copying its safety behavior. Attackers might want a model that behaves like yours but without constraints, so they might extract the base capability and then fine-tune or modify it. Or they might try to replicate how your system refuses or filters, so they can build a competing system with similar guardrails. Either way, the model's behavior is what's being stolen. For beginners, the key is that model theft is not always a dramatic heist. It can be a slow, quiet scraping of behavior through an interface. That makes prevention an operational discipline, not just a one-time hardening step. Query limits are one of the most practical defenses because they directly reduce the attacker's ability to gather data. When you limit queries, you raise the cost of extraction by limiting how many input-output pairs the attacker can collect. This can include rate limiting, which restricts how many queries can be made in a given time window, and quota limiting, which restricts the total volume of usage. It can also include per-user limits and per-tenant limits so that an attacker cannot simply spin up one account and scrape endlessly. Query limits are not a perfect defense because attackers can distribute queries across many accounts or many networks. But limits still help because they introduce friction and create detection opportunities. They also make abuse more visible because large-scale extraction requires abnormal usage patterns. Beginners should think of this like preventing web scraping. You cannot stop every scrape, but you can make it harder and easier to detect. The goal is not to make extraction impossible, but to make it expensive and risky for the attacker. A related defense is throttling based on behavior, not just raw volume. If a user sends many prompts that look like systematic probing, such as small variations around a template, that can trigger tighter limits. If a user requests unusually long responses repeatedly, that can trigger constraints, because long outputs provide more training signal for extraction. If a user attempts to harvest specific kinds of structured outputs, such as requesting the model to answer thousands of multiple choice items or to output consistent labels, that might also be suspicious depending on your use case. Behavior-based limits require careful tuning, so you do not punish legitimate heavy users, but they can be effective at reducing extraction efficiency. Beginners should see that the defender is trying to recognize the difference between organic usage and programmatic harvesting. Organic usage tends to be varied and goal-driven, while harvesting tends to be repetitive and coverage-driven. When you detect coverage-driven behavior, you can slow it down, restrict it, and investigate it. Limiting output information is another important part of query-based defense. If a system exposes internal confidence scores, token probabilities, or other detailed signals, it may give attackers more efficient extraction tools. Even exposing exact refusal reasons or detailed policy traces can help attackers understand how to evade defenses and replicate behavior. In general, the more diagnostic information you expose, the easier it is for an attacker to learn the model's structure through observation. This does not mean you should make the system unhelpful or opaque. It means you should design responses so they satisfy users without providing a tutorial for adversaries. In some settings, you might provide simplified outputs or constrain response formats for high-risk endpoints. You might also standardize certain behaviors so that responses leak less about internal state. For beginners, this is the idea of reducing the attack surface of the interface. The interface is what the attacker can see, so controlling what it reveals is a defense lever. Now let's discuss watermark strategies, which can sound like a magic solution but are best understood as one layer in a broader defense. A watermark is a detectable pattern that can be embedded into outputs so that later you can identify that the content came from your model. In a physical world analogy, a watermark on paper does not stop someone from copying the document, but it can help prove where the copy came from. In AI, watermarking might embed subtle statistical patterns in generated text that are difficult to notice casually, but can be detected by a verifier. The goal is attribution. If someone claims their model is independent, but their outputs consistently contain your watermark pattern, you have evidence of copying or misuse. Watermarking can also be used to detect when your outputs are being republished at scale, which can be a clue that someone is scraping. Beginners should understand that watermarking is more about detection and deterrence than prevention. It can raise the legal and reputational cost of theft, and it can provide a signal for enforcement, but it does not, by itself, stop an attacker from attempting extraction. Watermarking also has limits, and beginners should be aware of them because overtrust is dangerous. One limit is robustness. A watermark might be weakened by editing, paraphrasing, translation, or summarization. Another limit is that attackers who know about watermarking may attempt to remove it by post-processing outputs or by mixing outputs from multiple models. Another limit is false positives and false negatives, because detection depends on statistical evidence and thresholds. If a watermark detector is too strict, it may miss stolen outputs. If it is too loose, it may accuse innocent content. This does not mean watermarking is useless. It means it must be treated as evidence with uncertainty, not as an absolute proof. Watermarking works best as part of a system that also uses access control, query limits, monitoring, and legal agreements. For beginners, the key takeaway is that watermarking helps you answer the question of provenance, but it does not replace the need to protect the interface from being abused. Another practical defense is to segment capabilities and offer different access tiers. If some endpoints provide high-value specialized behavior, you can restrict them more tightly, require stronger authentication, and monitor them more aggressively. You can also design the system so that sensitive capabilities require interactive usage rather than bulk usage, making automated extraction harder. In some cases, you might provide summaries rather than full outputs for certain queries unless the user has a verified need. You can also use canary prompts internally, which are special prompts designed to detect scraping patterns. For instance, if you see many requests that resemble your canary set, that can indicate automated harvesting. Beginners should see that prevention is often about shaping the environment so attackers cannot efficiently operate. You do not need to block every request. You need to block the patterns that enable large-scale copying. This is similar to defending against data exfiltration. You focus on volume, repetition, and unusual access paths. It is also important to connect extraction risk to business and security outcomes. From a business perspective, model theft can undermine the investment made to develop the model and can reduce competitive advantage. From a security perspective, theft can enable attackers to study the model offline and find weaknesses, including how to bypass safeguards. It can also enable a malicious actor to use your capability for harmful purposes without your monitoring and controls. If your model is used in a security workflow, theft could allow attackers to learn how the model flags threats and then tailor their behavior to evade detection. If your model supports internal operations, theft could expose internal assumptions and domain knowledge. Beginners should notice that this is similar to the theft of detection rules or internal playbooks. Once stolen, attackers can adapt. So preventing model theft is not only about protecting intellectual property, but also about protecting the security posture that depends on the model's behavior. To close, preventing model theft starts with understanding that an AI interface can be used as a training data source by an adversary, allowing them to extract a substitute model through enough input-output pairs. Extraction is easier when queries are unlimited, outputs are richly informative, and behavior is highly repeatable, and it becomes harder when you limit volume and reduce observable signals. Query limits, including rate limits, quotas, and behavior-based throttling, raise the cost of scraping and create opportunities to detect abuse. Watermark strategies add deterrence and attribution by embedding detectable patterns in outputs, though they have real limits and should be treated as one layer among many. Strong access control, capability segmentation, monitoring for scraping patterns, and careful output design further reduce extraction efficiency and risk. The beginner mindset to carry forward is that protecting a model is like protecting any valuable service. Control access, watch usage, limit what the interface reveals, and build evidence mechanisms that help you respond when someone tries to take what they did not earn.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.